Section: Introduction. In this section, we discuss the challenges faced by large language models, LLMs, with long context capability, such as GPT-4, Gemini, and LWM, and their applications in chatbots, vision generation, and financial analysis. One major challenge is efficiently serving these LLMs without losing information. Due to the way LLMs work, loading the entire key value, KV, cache and model parameters into GPU SRAM for every token generated leads to low utilization of computational cores. The memory footprint of the KV cache, which grows with the sequence length, also poses a bottleneck for long sequence generation. Various methods have been proposed to address these challenges, such as KV cache eviction strategies that selectively discard KV pairs based on certain rules to limit the memory usage. However, these strategies may lead to information loss and issues like hallucination and contextual incoherency, especially in long contexts. Another approach called speculative decoding aims to speed up LLM inference by using a smaller draft model to predict the next tokens, which are then verified by the main model. But training these draft models to match the context length of the main LLM and ensuring accurate predictions pose significant challenges. To overcome these challenges, we introduce a hierarchical speculation approach that addresses the memory bottlenecks sequentially using different draft models. We also leverage attention sparsity within the KV cache and exploit contextual locality to improve drafting efficiency. Our system, TRIFORCE, integrates retrieval-based drafting and hierarchical speculation to accelerate inference for LLMs with long contexts in both on-chip and offloading scenarios. By maintaining the full cache and using superior KV cache selection methods, TRIFORCE ensures lossless retrieval of context information. We demonstrate the effectiveness of TRIFORCE through extensive experiments and ablation studies, showing significant speedups compared to baseline models. TRIFORCE achieves impressive speedups on different GPU configurations and can efficiently handle long contexts while maintaining high acceptance rates and scalability. Section Summary. In this section, we introduce TRIFORCE, a speculative decoding system designed to efficiently serve large language models, LLMs, with long contexts. TRIFORCE leverages hierarchical speculation to address memory bottlenecks in model weights and key value, KV, cache, achieving up to 2.31 times speedup for Llama 2 to 7B128K on a single A100 GPU. By utilizing retrieval-based drafting and hierarchical speculation, TRIFORCE demonstrates robustness and scalability, outperforming other methods like streaming LLM and H_2O, making it a promising solution for accelerating LLM inference tasks. Section: Background. In this section, we discuss speculative decoding, KV cache eviction strategies, KV cache quantization, observations, analysis, and insights that have guided the design of our TRIFORCE model. Speculative decoding aims to speed up LLM decoding while maintaining output quality by using tree-based speculation methods to generate multiple token predictions simultaneously. KV cache eviction strategies, such as those used in streaming LLM and H_2O, prioritize retaining critical tokens for attention computation to ensure stable performance without increasing the context window size. These strategies focus on recent tokens and specific attention sink or heavy hitters, limiting the model's processing based on their eviction policies. Various approaches to KV cache quantization have been introduced to improve efficiency in long sequence generation by compressing the bit width of KV cache activations. Our observations reveal attention sparsity in pre-trained LLMs, suggesting that a fraction of the KV cache can serve as a draft cache for self-speculative decoding. By leveraging this sparsity, we can achieve high acceptance rates with a limited number of tokens. Our experiments show that information from long context tokens needed by adjacent tokens tends to be similar, allowing a single cache construction to suffice for multiple decoding steps. This amortizes the latency of cache construction and improves efficiency. Both streaming LLM and H_2O implicitly incorporate this principle by retaining high-scoring tokens and reusing local information, reducing the need for complete cache reconstruction. Section Summary. In this section, we introduce speculative decoding as a method to accelerate LLM decoding while maintaining the model's output distribution accurately. We also discuss KV cache eviction strategies like streaming LLM and H_20, which prioritize critical attention sync tokens to stabilize performance for handling infinitely long text sequences efficiently. Additionally, we explore KV cache quantization approaches and leverage observations on attention sparsity to optimize cache usage and boost efficiency in long context language modeling tasks. Section TRIFORCE. In this section, we introduce the TRIFORCE, which combines a retrieval-based KV cache selection policy and a hierarchical speculation system. We believe that our retrieval-based approach is more straightforward and accurate compared to other methods like streaming LLM and H2O. These existing methods struggle with maintaining detailed contextual information due to their ineffective cache updating strategies. To address this, we have designed a hierarchical system that targets the dual bottlenecks in speculative decoding, leading to a significant improvement in overall speed. Our experiment compared the performance of streaming LLM and H2O in a needle retrieval task, revealing a drop in their accuracy rates compared to their performance on the PG19 dataset. This highlights the limitations of these methods, which operate on a lossy principle by permanently discarding evicted tokens. In contrast, our retrieval-based method maintains the entire KV cache, allowing for more flexible cache selection. By segmenting the KV cache into smaller chunks and calculating attention between queries and key caches within each chunk, we can effectively identify and gather the most relevant information for the task. Furthermore, to address the latency introduced by loading whole model weights for drafting, we have implemented a hierarchical system that includes a secondary lightweight model with streaming LLM cache for initial speculations. This system reduces drafting latency by speculating for the target model using a draft cache based on retrieval-based methods. By establishing this sequential speculation hierarchy, we accelerate the overall inference process. In conclusion, TRIFORCE is designed to enhance the speed of LLMs for generating long sequences by addressing both model weights and KV cache bottlenecks. The pseudocode for TRIFORCE involves pre-filling the target model with full cache and the draft model with streaming LLM cache, constructing the retrieval cache, and updating it based on contextual locality insights. The inference process iterates until the target sequence length is reached, with each iteration involving 2 speculations to address both bottlenecks effectively. Section Summary. TRIFORCE introduces a retrieval-based drafting approach that outperforms existing strategies like streaming LLM and H_20 by preserving detailed contextual information through a lossless cache selection policy. Additionally, a hierarchical speculation system is implemented to address bottlenecks in speculative decoding, improving overall speedup by efficiently managing model weights and KV cache. By focusing on relevance rather than recency, the retrieval-based method excels in handling contextually dense datasets, while the hierarchical system reduces drafting latency and accelerates inference. Section: System Implementation. In this section, we implemented the draft and target models using transformers. By utilizing a predetermined cache budget, we effectively utilized PyTorch CUDA graphs, which helped minimize kernel launching overhead during speculative decoding. Flash attention was employed to speed up attention operations. We maintained full layer sparsity without excluding the initial 2 layers to ensure system efficiency within the fixed KV cache budget. Although this approach may result in a lower acceptance rate, the constant drafting cost makes it a worthwhile compromise. Additionally, we implemented 2 extra speculation cache structures, including a retrieval cache and streaming LLM cache, to facilitate a faster speculation phase. Our goal in this section is to demonstrate the capabilities of TRIFORCE, a scalable and robust speculative decoding algorithm designed to accelerate the inference of LLMs for long sequence generation, significantly reducing the wall clock time. We showcase the overall speedup achieved by our end-to-end system in both on-chip and offloading settings, followed by detailed ablation experiments. TRIFORCE achieved up to a 2.31 times speedup for Llama 2 to 7B 128K on an A107.78 times on two RTX 4090 GPUs with offloading, reaching a latency as low as 0.108 seconds per token. Our results also demonstrated that TRIFORCE enhances large batch inference efficiency by 1.9 times. We conducted detailed studies on the KV cache budget and chunk size to provide insights into selecting appropriate hyperparameters for maximizing efficiency. Additionally, we discussed the compatibility of TRIFORCE with tree-based speculative decoding. We conducted experiments based on Llama 2 and LWM models with a 128K context window size, utilizing a 4K retrieval cache as an intermediate draft cache in our hierarchical system. For offloading experiments, we aim to maximize memory utilization by offloading the remaining KV cache to the CPU while keeping the model weights on the GPU. Our evaluation was performed on the PG19 and narrative QA datasets, testing on 100 examples with specific prompt lengths and token generation goals. We analyzed the performance of TRIFORCE across various hardware configurations, including on-chip experiments on an A100 and offloading experiments on RTX 4090 GPUs. Considering the challenges of training a draft model with long contexts, we used JF68M with streaming LLM cache as a naive policy approach. We experimented with various temperatures to test its robustness. Our evaluation of TRIFORCE using different temperatures showed significant speedups for both on-chip and offloading settings. For instance, TRIFORCE achieved up to a 2.31 times speedup for the on-chip setting with a minimal 4K KV cache budget for Llama 2 to 7B 128K. In offloading settings, TRIFORCE efficiently served various models on consumer GPUs, demonstrating substantial speed improvements compared to highly optimized offloading systems. TRIFORCE also boosted the efficiency of batched inference, achieving a 1.9 times speedup for a batch size of 6 with each sample having 19K contexts. Section Summary. In this section, we implement the draft and target models using transformers, utilizing a predetermined cache budget to minimize kernel launching overhead during speculative decoding. Flash attention is employed to accelerate attention operations, maintaining full layer sparsity for system efficiency. Despite potentially lower acceptance rates, the constant drafting cost proves to be a valuable compromise, supported by the implementation of 2 extra speculation cache structures for faster speculation phases. Section: Analysis. In this section, we analyze the effectiveness, scalability, and robustness of TRIFORCE. Firstly, we observe that TRIFORCE's integration of the hierarchical system boosts speedup significantly compared to other methods. TRIFORCE outperforms both the streaming LLM method with hierarchical speculation and the retrieval method without the hierarchical system. Regarding scalability, as shown in the speedup versus context figure, TRIFORCE exhibits excellent scalability with longer context lengths. This scalability is due to its high acceptance rate and the increasing gap between the draft and target model latencies. Theoretically, TRIFORCE could achieve a speedup of up to 13.1 times, which is 7 times higher than the naive policy, showcasing its substantial scaling potential. In terms of robustness, unlike traditional speculative decoding methods, TRIFORCE maintains consistent performance across different temperature settings. It shows less sensitivity to temperature changes, with an acceptance rate above 0.9 even at a temperature setting of 1.0, demonstrating its stability and reliability. Moving on to the ablation results, we conducted extensive studies focusing on 3 main aspects: the impact of different KV cache budgets, the influence of chunk size selection, and TRIFORCE's compatibility with tree-based speculative decoding. For the KV cache budget, we found that increasing the cache size up to 4K improves the acceptance rate for TRIFORCE. However, further expansion beyond 4K may not provide significant benefits due to increased drafting latency. Therefore, setting the KV cache budget at 4K is the most effective strategy to balance a high acceptance rate with minimal drafting overhead. Regarding KV cache chunk size, we discovered that selecting smaller sizes may lead to overfitting on individual tokens, while larger sizes risk neutralizing high-score tokens with low-score ones, limiting selection flexibility within a fixed budget. Lastly, we explored the compatibility of TRIFORCE with tree-based speculative decoding methods. By combining TRIFORCE with tree structures like Sequoia and independent sequences, we found that this integration could potentially enhance the overall end-to-end speedup by utilizing additional speculation budgets.